Hi students, welcome back to the class. In the previous classes, we were discussing about potential energy. Now we have a clear idea about what is the potential energy for electric charges, right? And we also learned about how to calculate this potential energy for a system of 2-point charges and for a system of 3-point charges. And today we are going to find the potential energy of a dipole in a uniform electric field. A dipole. What is a dipole? Dipole is a system of two equal and opposite charges separated by a small distance. And uniform electric field means the value of electric field will be the same at every points. Okay. So today let us see how to calculate this potential energy of a dipole in a uniform electric field. Okay. And I will draw the figure. This is our figure. You can see our electric dipole, that is we have a negative charge and a positive charge separated by a distance 2a. And this electric dipole is placed in a uniform electric field E, and the dipole moment P makes an angle theta with the uniform electric field E. And we know when a charge is placed in an electric field E, that charge will experience a force F, and we know the magnitude of that force. We have this equation: electric field E is equal to force by charge. So what is the force experienced by that charge? F is equal to Q into electric field E. F is equal to Q into E is the force experienced by a charge Q when that charge is placed in an electric field E. So we have two charges, minus Q and plus Q, and these two charges are placed in our electric field E. So these two charges will experience a force. And what is the force experienced by the negative charge? It is minus QE. It is minus QE, and the positive charge will experience a force plus QE. I will draw that two forces in the figure. This is minus QE, the force experienced by the negative charge, and this plus Q experiences a force plus QE along this direction. And you can see that the magnitude of these two forces are same, but they are acting in the opposite direction at 2 points. And what is the name given for such forces? That is, two equal and opposite forces acting at two ends are known as couple. So here our electric dipole, when placed in an electric field, experiences two equal and opposite forces plus QE and minus QE act on its two ends. These two forces are acting at the two ends of the electric dipole, and the two forces form a couple. Couple means two equal and opposite forces acting at two different points. So we know instead of a force, the electric dipole will experience a torque. And let us find the torque exerted by the couple. Okay. The torque exerted by the couple, we know torque is equal to force into perpendicular distance. And the magnitude of the force is QE, and in the figure the perpendicular distance is BC. That is, when you consider this right angled triangle, the perpendicular distance is BC. So torque tau is equal to QE into the perpendicular distance BC. And consider this right angle triangle ABC to find this side BC. For that we take sine theta. Sine theta is opposite side, that is BC. Opposite side is BC and hypotenuse is 2A. So sine theta is equal to BC by hypotenuse, that is 2A. Therefore, perpendicular distance BC will become, BC is equal to 2A sine theta. And let us write down this 2A sine theta here. So torque will become, tau is equal to QE into 2A sine theta. And we already know Q into 2A is dipole moment P. So here we can write tau as PE sine theta. Why? Since P is equal to Q into 2A. So this is the torque exerted by the dipole when it is placed in a uniform electric field. But we are trying to calculate the potential energy of a dipole, right? So this is not enough. This is only the torque exerted by the couple. Okay. So now let us try to calculate how we calculate the potential energy of this dipole. So we think how we calculate the potential energy of this electric dipole. We know potential energy is the work done in assembling the charges from infinity to a particular point. Thus, that is how we define potential energy. Potential energy is the work done. So look at this. Consider this as our electric dipole, and that electric dipole moment makes an angle theta with the electric field. Suppose this dipole is rotated through a small angle d theta, that is, this is the current position of the electric dipole. Now we are trying to rotate that electric dipole through a small angle d theta, and we are trying to rotate this electric dipole against the torque acting on it. So we have to do some work because we are trying to rotate the electric dipole against the torque. So anyway we have to apply some work. We have to apply some work in order to rotate the dipole through a small angle d theta. So from that we can calculate the work done in order to rotate the dipole through a small angle d theta. So the small work done to rotate the dipole through small angle d theta can be written as dw. Work is equal to force into displacement. Here force can be written as torque into the displacement. Here the displacement is d theta, and tau is PE sine theta. So it is PE sine theta into d theta is the small amount of work done to rotate the dipole through a small angle d theta. This is only the small amount of work done to rotate the dipole through d theta. Imagine if the dipole is rotated from theta 1 to theta 2. Then we can calculate the total work done in rotating the dipole from its orientation, making an angle theta 1 with the orientation of the field to theta will be, that is, the total work done can be calculated by integrating this small work done from theta 1 to theta 2, because it is rotated from an orientation theta 1 to theta 2. So we can calculate the total work done by integrating this small amount of work done. So the total work done can be written as W. W is equal to integral theta 1 to theta 2 dW. And let us substitute dW as PE sin theta. So it is theta 1 to theta 2 PE sin theta d theta. Then we are going to integrate this. P, E are all constants. We can take that outside the integral sign. So it is PE integral theta 1 to theta 2 sin theta d theta. Then what is integral sin theta d theta? Integral sin theta d theta is equal to minus cos theta. So after integrating the sin theta, we will get minus cos theta. Minus can be written here, and cos theta, limits from theta 1 to theta 2, and apply the limits, upper limit minus lower limit. So this will become minus PE into cos, upper limit is theta 2. So it is cos theta 2 minus cos theta 1. And we can make a small rearrangement, so this negative sign can be removed. That is, I will write cos theta 2 minus cos theta 1 as minus cos theta 1 minus cos theta 2. So negative of negative will become positive. So this can be written as PE into cos theta 1 minus cos theta 2. So this is the work done. Work done in rotating the dipole from theta 1 to theta 2. And this work done is stored as the potential energy U. So we know potential energy is the work done. So this work done can be written as the potential energy U, and U is equal to PE into cos theta 1 minus cos theta 2. Cos theta 1 minus cos theta 2. Okay. Here we consider our electric dipole makes an angle theta with the electric field. This is what we have considered here. Imagine initially the dipole is oriented perpendicular to the direction of the electric field. So initially this is the alignment of the electric dipole. So what is the angle theta 1 here? Theta 1 is 90 degree here. If initially the dipole is oriented perpendicular to the field, then it is rotated through an angle theta. So here theta 1 can be taken as 90 and theta 2 can be taken as theta when initially the dipole is oriented perpendicular to the field, and after that it is rotated through an angle theta. So here theta 1 can be written as 90 degree and theta 2 is equal to theta. Okay, so let us substitute these values here. So the potential energy will become U is equal to PE into cos 90 minus cos theta. What is cos 90? Cos 90 is 0. So it will become PE into minus cos theta is potential energy in this case. And what is PE cos theta? It is P dot E. That is AB cos theta is equal to A dot B. So PE cos theta is equal to P dot E. P cos theta equal to P dot E. So this can be written as minus P dot E. Minus P dot E is the potential energy. So these are the two equations for potential energy.